So this is one of the another AP exam questions that College Board posted for you, and I thought I would go over it before you take AP exam. Also, try to read the question, pause it, and try to solve it. If there are additional links underneath the video that I probably will during the video will tell you, you probably should watch if this troubles you somehow. So watch those videos before or after. I will post before or after videos, so take time to watch them and then come back to the problem if you cannot solve it. But if you can solve it, try to solve it. Even if you make mistakes, you're still learning from them. So here's another question. A company selling a type of spring makes the following claim: the elastic potential energy that the spring is capable of storing for a given compression distance does not decrease even after the spring compresses and or stretches hundreds of times. The students in a physics class have decided to test the company's claim. So for the first part, A, state the basic physics principle of law the students should use in designing an experiment to test the company's claim. Using the principles or laws stated in Part A, first one, determine the equation for the elastic potential energy stored in the spring in terms of quantities that can be obtained from measurements made with equipment usually found in a school physics lab. So for the first part, let's look at the statement. It says that elastic potential energy that the spring capable of storing, no matter how many compressions happens, will not decrease and stay the same. So when they say state the basic physics principle or law the students could use in describing the experiment or test company's claim, you could say that you could use conservation of energy to test that principle. And how you would do this, you would stretch the spring a certain distance x and calculate the potential energy of the spring. So the potential energy of the spring would be 1/2 kx squared, and x is the part that you stretch. And then you would check that your kinetic energy of the block that you attach to it, kinetic energy of the block, when the spring reaches its equilibrium, is equal to 1/2 mv squared. And so if they are equal to each other, then energy is conserved. And also, no matter how much you stretch the spring, the energy would always be conserved. So then that means that no matter how much you stretch the spring, it doesn't lose its quality of storing potential energy, and always transfers all that energy into the kinetic energy. For B, they say design an experimental procedure the students could use to collect the data needed to test the company's claim. Assume equipment usually found in a school physics lab is available. In the table below, list, or on our side, it's still below, list the quantities and associated symbols that would be measured in your experiment and the equipment used to measure them. Also, list the equipment that would be used to measure each quantity. You do not need to fill in every row. If you need additional rows, you may add them to the space just below the table. Describe the overall procedure to be used, referring to the table. Provide enough details so another student could replicate the experiment, including any steps necessary to reduce experimental uncertainty. As needed, use the symbols defined in the table and or include a simple diagram for of the setup. So there could be different ways to set up this experiment. You could, as we said earlier, you could use potential energy transfer to the kinetic energy. So the equipment you would use is the ruler. So the first one is asking you the quantity to be measured. So you need the distance stretched, right? Distance by which you stretch. The equipment for measurement is the ruler. And the symbols is going to be X. And then you need a motion detector to actually the quantity to be measured, velocity, right? So the distance is on the top. And then you need the velocity. And that's going to be, you need the maximum velocity. And you need motion detector. To measure that one. So you could do it this way. So every time you would stretch it many times, or stretch or compress, whichever it is. Measure by how much you're stretching or compressing, and then calculate the velocity. And you need the block, right? So you quantity to be measured. You don't need to measure the block. You need 1/2 mv squared. You just need to know the mass of the block. You don't have to change the block every single time. You want that to stay consistent. You don't want to change the blocks every single time. So you need 1/2 kx squared and 1/2 mv squared. So you need x and you need v to calculate that. That is one of the ways. And the other way you could do this, and we could mention this also in part A, so you could do this method, conservation of energy, or you could do an experiment where you use, so this is one of the way, this is completely different way, the next one. Let me change the color. So for the next one, I need the quantity to be measured, force, and what I'm measuring is F, and then I also need to measure the distance you're going to be compressing, so you still need distance, so you measure an X. So for that one you need a ruler, and this one is force scale. And so what you're gonna do is you're gonna compress the spring as many times as you want to different distances x. So every time you just change different x. And if you use this, F is equal to kx. So every time you compress, you're gonna get a certain distance compressed, and it will give you force reading on the force scale. And from here you can see what k is equal to. Then again you're going to compress to different x, and it will show you what the force is, and you know by how much you compressed you still should get the same k. And you do it many times and see that your k stays unchanged. So every time you do this, your k should be the same. Then that means it doesn't matter how much you stretch and how much you compress, it always gives you consistent k. For C, they ask you explain how the students should analyze the data to determine whether the company's claim is true or not, whether the energy stored by the spring for a given compression distance does not decrease after the spring has been compressed or stretched hundreds of times. And here you just repeat again yourself. If you do 100 different measurements, you compress the spring a certain amount, so you still have to do, you would have to write it down. You would say that you compress the spring 100 times, you detect potential energy, then you measure the velocity, maximum velocity every single time, And if your energy is always conserved, that means the spring did not lose its quantities. It still has the same spring constant K, and holds the claim that energy is not lost and all the potential energy stored every single time stays the same. So your relationship between potential energy and kinetic energy would stay the same. And then for the second part, like if you chose to do kx is equal to, no, F is equal to kx. So if you chose the other one, the other example, F is equal to kx. Again, you can do 100 times. You measure the force and the distance you stretch every single time. And if your K stays consistent, then again, you do not lose energy in the system. But you have to do 100 times without changing anything. Just keep measuring, and every time K should come up the same. So that would be the answer for C. Often when they give you such big problems on AP exam, they're not necessarily difficult. They are very conceptual, and it looks scary to have such a big problem. Just read it a few times to make sure that you understand what they ask you. And so for the D part, the students also investigate two springs, spring A and spring B, made by another company. The students hang spring A vertically, attaching blocks of various known masses from the bottom end of the spring and measuring the total length of the spring for each block. The students graph the spring length as a function of hanging mass and draw the line for the best fit as shown above. So we have the graph shown above. I'm going to come back after I'm done reading. So for the first part, they say students follow the same procedure using spring B, and which has the same equilibrium length as A, but stores more energy than spring A. For the given displacement, on the graph above, sketch what the line of best fit could look like for the data obtained using spring B. So spring B stretches the same distance, but has the same equilibrium, but has more energy. So it looks like the second spring B will have the same equilibrium length as A, but stores more energy than A. So I can write, let me bring this up. I can write this way. Potential energy of the spring A, let's say, is equal to 1/2 kx squared. And potential energy of spring B is equal to 1/2 kx squared. They tell me that they stretch the same, but B has more energy. For B to have more energy, you have to have K with more energy. So let's go back to the graph right here and see. Spring length and mass hanging. I have a relationship. So F is equal to Kx. And looks like, and the force is acting is mg because they're hanging the mass. So they tell you the mass, and this is the length. So I have in my graph, I have this is my y-axis, and this is my x-axis. So I could rewrite this formula as x is equal to g over k m, and this is my slope. So I have y is equal to mx plus b. My b would be the y-intercept is 25 here, but I need the stretch of the spring. So I see that my g over k is my slope. So g over k is my slope. And from this equation, I see that b must have a larger k. So if B has a larger K, then the slope of the new graph is going to be smaller, because this is your y, this is your x, and this is your slope. And because K in B is bigger, the slope of the graph is going to be smaller. So that would be the graph for B. And for the last part, they say the students attach a block to spring B and let it hang at rest. The students pull the block down by 1 centimeter, release it, and measure the time interval for one oscillation. The students then repeat the procedure but pull the block down by 2 centimeters instead of 1 centimeter. Which would initial displacement if either? For which initial displacement if either is t greater? So it's block B, and we know block B has spring B, and it has greater K. So I have its oscillation when you stretch the spring and let it oscillate back and forth. So I can calculate the period of such oscillation as 2 pi, so the spring formula, and I have m over k. And from this I see that my time of oscillation, they ask you for which initial displacement if either t is greater. My t does not depend on displacement. Doesn't matter, I pull it by 1 centimeter or 2 centimeters or 5 centimeters. The force is going to be acting different because force is equal to kx. But my time does not depend on it. My time depends on the mass. And the students attach a block to spring B and let it hang, but they don't change the mass. Mass is the same. And K is already given. We said it's going to be a little bigger than A. Bigger than A. So the answer for this one is going to be T is the same for both cases.